Hello everyone, this is our lesson 3 physics 30 class notes, and again this is a review of the physics 20 concepts. This time we're looking at energy or energetics. So just a quick recap then, you'll be familiar with this formula once on your data sheet. It's really just this idea that work can be done by a force, and that force can be a force applied, it can be a force of friction, it can be any force. It just has to be applied for a distance. Okay, now this FD cosine theta formula is considering a force being applied at an angle. So if this is our mass, and the mass is going to be dragged along this distance, so it's moving a horizontal distance, it's possible to do that with a force applied at an angle, and that's where we would use this FD cosine theta. So it's just a recap there from physics 20. Of course, if you want to think about it a little bit more, then we get into our SOHCAHTOA stuff, and we can think about the cosine of the angle here being equal to the adjacent and the over the hypotenuse. Okay, so the hypotenuse here, of course, being the force, and so we can bring that up to the side. The force is the hypotenuse, so this is the hypotenuse here. This is the adjacent. So the force applied, cosine theta, well, that's going to be equal to the work done, and that's where it comes from. And you just have to multiply it then by the d. So hopefully that's a recap. Of course, more simply, we can think about forces being applied and going in the same direction as the object. So in this case, horizontally applied, going in the same direction as the object. We can think about forces that are opposite to the direction of the motion. In this case, we would have our negative sign coming in because we have to take into account the forwards and backwards nature, or the positive direction, negative direction. If we do happen to do some, if we happen to apply a force that is perpendicular, then it's worth noting that this would, if we did this on pure physics, we would work this out to be zero work done. So it's kind of a weird one. I mean, even if you were carrying something very heavy, it might feel like you're doing lots of work, and you're just holding the object at a fixed height. If you then walked with that object, it may feel like you're doing lots of work, but in terms of the physics, you're not doing any work at all because the force you're applying is perpendicular, and therefore you're going to get a zero. Anyway, we'll take a look at a few questions, and hopefully it'll be a little bit more clear when we start putting some values in. Okay, so first scenario here, we have a 240 Newton force pulling a 10 kilogram sled to the right at a constant velocity. So once again, we're thinking about our physics principles. This is very important here. Our physics principle here is 0. This means my F net is 0. This is my big idea here. This means I'm going to have balanced forces. I've got this uniform velocity. Let's go ahead and do a little free body diagram. So here's my object. It's a sled. I'm applying a 240 Newton force. So I'm going to go ahead and say that this is to the right. So this is my force applied, and that's 240 newtons. There's a constant velocity, so this is moving out of v being equal to 3. So it's moving at 3 meters per second to the right. And I need to know the amount of work done by friction in 8.5 seconds. So there will be work done by friction. If I was to put my frictional force on here, it's going to be equal and opposite to the force applied. How do I know it's equal and opposite? Well, because if I did an F net, my F net would be equal to 0. In fact, let's just quickly do that. My F net, which is the sum of all forces, this is going to be equal to 0. The acceleration is 0, so my F net is 0, and this tells me now that my force applied plus my force of friction need to be equal to each other. Okay, so they're going to be equal and opposite. Okay, so to solve this, to figure out the work done, I'm going to think about the work done by the force of friction, and I know that's going to be a negative force. I'm going to say that this side of my diagram is negative, this side is positive, so I can see that that frictional force is negative. So it's going to be negative frictional force multiplied by the distance it moves. Okay, so I need to find this distance here. How do I do that? Well, I know I've got time and I've got a constant velocity. So my physics principle 0 tells me that I can find this velocity if I know the distance and the time. In other words, I can find the distance if I multiply my velocity by time. And since I know my velocity and I know my time, that's going to give me my answer. So 3 meters per second multiplied by a time of 8.5 seconds, that's going to give me the displacement. So that gives me a displacement of 25.5 meters. So I'm going to add this on. This sled is moving a distance. The distance this moves is 25.5 meters. Okay, so the force of friction is going to be working against that during this time period, and that's what I'm trying to find out. That's the work that I'm trying to calculate. So let's go ahead and finish this off. I've already said that the work done by the force of friction is going to be equal to this negative force of friction. Negative force of friction times this distance. Okay, so let's go ahead and figure this out. Now, it's worth knowing that work, of course, is a type of energy, and energy can't be negative. It's a scalar value, so I'm not really that concerned about the negative sign. So the work done by friction, this work done by friction, is going to be equal to the force applied by friction. Well, the force applied by friction is equal and opposite to the force applied. So I know this is going to be 240. So 240 newtons. Actually, I should put the newtons on there. Let's just add that newton to here. So there it is, 240 newtons, multiplied by now the distance that I just calculated, which is 25.5 meters. Okay, and that gives me the work done to be 6,120 joules. So just to keep track of the significant digits, work done by the force of friction is going to be 6.12. I'm just going to use 3 significant digits because every value in my question was 3 significant digits. So there's my 3 significant digits right there. I'm going to say that's 3.12 times 10 to the, well, my decimal point has to move 1, 2, 3, so times 10 to the 3 joules. Okay, so for example 2, we start getting into the different types of energy. And so you'll remember from physics 20, we have kinetic energy and gravitational potential energy to think about. And that means we can start talking about conservation of mechanical energy. Of course, we could also add the spring energy from Hooke's law, so half kx squared, that could come into this. And in physics study, we'll learn about some other types of energy as well. We'll talk about electrical energy and EMR energy as well. Oh, and of course, mass equivalence energy. But for now, we're just recapping our physics 20. Also to note is our unit conversions, these fundamental units. This is going to be really important too. We'll definitely be talking about unit conversions. The diploma will always have one question asking you to rearrange, look at the fundamental units or the SI units or the equivalent units, that kind of stuff. So in this case, it's always worth remembering that 1 joule is a kilogram meter squared over second squared. And if you're not sure, if you forget that, then I would suggest thinking about the most memorable, probably the most memorable energy way back from Science 10 is this gravitational potential energy, which is mgh. And of course, you can just go ahead and put the units in for this. So kilograms, and then g is an acceleration, so that's going to be meters per second squared. And then you're going to multiply that by the height, which is another meter. So we're just multiplying meters by meters, so that's meters squared. So if you forget your energy fundamental units, just think of mgh, put in the units, and you should be good. Okay, let's look at this question. Okay, so here we have it. It's sort of a roller coaster question, or a cart rolling down a hill. We're going to be thinking about conservation of mechanical energy. So right away, I want to be writing this out as a bit of a statement. I'm going to put it over here. So I'm going to say the sum of the energy initial is going to be the sum of the energy final. Again, very important concept. We're going to be using this a lot in Physics 30. It's linked into the work energy theorem, and it's a physics principle that keeps coming back again and again. It's a big one. So let's look at what we have. So we've got this cart at the top of a hill. Okay, now it's worth giving us a reference point. So clearly this dotted line is meant to equal the ground. So let's call this 0 meters. This has a height of 0 meters. This is going to be my reference point. So if you happen to be on this reference point, that means you have 0 height, according to my definition here, and that means you'll have 0 potential energy. Initially, though, the cart is at the top of the hill. So this cart will have some gravitational potential energy, EPG, you can tick that off. And it's also got a velocity, so it's also got an EK, tick. When it gets to the bottom of the hill, it's going to lose all of this gravitational potential energy because I've defined this to be 0. So at the bottom of the hill, its gravitational potential energy is going to be 0. Whereas it's now going to have, probably, you can think about this, it's probably going to have a bigger kinetic energy at the bottom of the hill. Okay, a couple of assumptions here. In the previous lesson, we talked about friction and the work done by friction. In this question, we can go ahead and assume that there's no friction here. Okay, so that's actually one of the assumptions, and we're going to just make a note of that here. One of my assumptions is that there's no force of friction. There's also going to be no force of air resistance. So I'm not going to lose any energy, of course, to heat or to sound. Okay, is this very realistic? No, but it's an assumption. And it's an important concept to think about, and it's important to state it initially. Okay, so let's go ahead and solve. I'm going to add up all of the energies that this system has before. So that's going to be at the top of the hill. This is before, or if you want to call it initial, that's fine, the initial state here. And then at the bottom of the hill, this is its after, or final state. Okay, so initially it has some gravitational potential energy, so I'm going to call that EPGI, okay, plus it's going to have some kinetics, so EKI. Okay, and that all is going to equal the final values of these, so potential gravitational final energy plus the kinetic final energy. Now, we've already said that at the bottom of the hill there's going to be no height, in other words 0 meters height, which is going to give us a 0 value for the potential energy, so I can cancel that out. So I'm going to have an equation here. I'm going to have mgh initial plus 1/2 mv squared initial is going to be equal to 1/2 mv final squared. Don't forget the squared. And I'm pretty much ready to solve. The only nice thing too is I can cancel out all my masses. So I can end up writing a statement GHI plus 1/2 VI squared is equal to 1/2 VF squared. And I can put my values in, so let's just do this, 9.81 meters per second squared times the height, which is 6.1 meters, plus, well, but this is 0.5 plus 0.5 times the initial velocity, which is 5.3 meters per second, and that is squared. And that's all going to be equal to 0.5 times the final velocity squared, and that's what I'm trying to calculate. So the final velocity is going to be the square root of, if you do the calculations, you're going to get 73.880, keeping all the digits in my calculator, over 0.5, and that's going to give you a value of 12 meters per second. And I just want to state that that's to the right of the page. Okay, just checking my significant digits quickly, looking back at the question. Yeah, 2 significant digits here, 2 significant digits here. That matches my answer. I'm good to go.